All right, we are continuing with two number relationships. Last lesson we did scatter plots. So we're going to continue with that, sort of figuring out if two values have a relationship and what their relationship is. First of all, not all relationships between two numerical values are linear. There are many solutions where the pattern in the scatter plot would be best described by a curve. Two types of functions often used in modeling non-linear relationships are quadratic and exponential. Quadratic would be a parabola that opens up or a parabola that opens down, on your graph. Exponential would be something that decreases exponentially or increases exponentially. So, first example. Sometimes the pattern in a scatter plot looks like the graph of a quadratic function, with the points falling roughly in the shape of a U that opens up or down, as in the graph below. In other situations, the pattern in the scatter plot might look like the graphs of exponential functions that are either upward sloping or downward sloping. That's our exponential. So let's look at these 5 plots and discuss them. Okay, we've got 5 different scatter plots. So let's look at them and see if we can figure things out. So you have these in your notes. The next slide's not going to have each picture, but you can refer back to your notes. So number 1, which of the 5 scatter plots in lesson 12 shows a pattern that could be easily described by a quadratic curve? So these 5 scatter plots are from lesson 12. So look for the one that sort of looks U-shaped. And if you see that scatter plot 4, you could draw a line through, a curvy line, through the dots that are shown there, and that would be a positive quadratic curve. Which of the 5 scatter plots shows a pattern that can be reasonably described by an exponential curve? I'm looking at them. Scatter plot 2 sort of shows a shape like that. Looking at all the other ones, that's really the only one that I see that fits that exponential curve, the decreasing exponential curve. Okay, still with lesson 12 information, let's revisit the data on elevation in feet above sea level and the mean number of clear days per year. The scatter plot of this data is shown below. The plot also shows a straight line that can be used to model the relationship between elevation and mean number of clear days. Again, like normal, I'm not sure what you did in grade 8. Some of you are in grade 8, some of you are in grade 7, so that's sort of irrelevant for what we're talking about. But in a previous math course, you informally fit a straight line to model the relationship between two variables. The next lesson shows a more formal way to fit a straight line. That's where we're going to do some things with our calculator, which I talked about last lesson a little bit. The equation of this given line, the one they drew here, is y equals 83.6 plus 0.008x. Just like normal, this right here is your slope, and that right there is your y-intercept. Okay, if you look, that looks to be in the 80s somewhere, so it's your y-intercept. Right, assuming that the 14 cities used in this scatter plot are representative of cities across the United States, should you see more clear days per year in Los Angeles, which is near sea level, or in Denver, which is known as the Mile High City? Justify your choice with a line. Justify your choice with a line showing the relationship between elevation and mean number of days. If you look at this, I would say Denver, since the number of days increases, it's a positive slope, as elevation increases, right? If you look back at the previous lesson and the data that was given, I just pulled it up to look back at it. It looks like Los Angeles has about 84 clear days, and Denver has about 125 clear days. That's from the chart in lesson 12. From the linear model, which is a line, 83.6.008x. From the linear model, Los Angeles, which is at sea level, so if I do LA is at x equals 0, we have y equals 83.6. Okay, so this one here represents at sea level, x equals 0, your elevation equals 0. The number of clear days equals 83.6. If I look at Denver, which is the mile-high city, so we have x equals 5280. I'm going to plug that in, y equals 83.6 plus 0.008, so yep, 2 zeros, times 5280. I'm going to get my handy-dandy calculator out, crunch some numbers, and that gives me y equals 125.84 days, which is pretty spot on the chart from the previous lesson. So our linear model, which is what that is, that's our linear model. Our linear model is pretty spot on to what the chart showed for the actual data. Okay, one of the cities in the data set was Albany, New York, which has an elevation of 275 feet. If you did not know the mean number of clear days for Albany, what would you predict this number to be based on the line that describes the relationship? So we're going to use that model for the line and plug in the distance. Okay, that right there, handy dandy calculator, gives you the number of clear days to be about 85.8 days. So let's just round that to 86 days. And then Albuquerque, that has an elevation of 5,311 feet. So go ahead and plug that into the model, calculate it, and it looks like we have about 126 days. So was the prediction of mean number of clear days based on the line closer to the actual value for Albany with 69 clear days? So Albany, our prediction using the model, was 86 days. And our data, our real data, said 69 days. And then Albuquerque, we had a prediction of 126 days, in real life 167 days. So if we're analyzing that, really what this is going to show is the distance from the predicted line to the real dot. Okay? So the distance between the predicted line and the real dot is 17 units. The distance from the from the predicted line to the real dot is 41 units. So that just our smaller distance is a better prediction. Okay, the distance from the predicted point on the line to the point representing Albany is a smaller distance. So it's a better prediction. If you would look at the data, we have a line. Let's see, that line looks like this. So when I have an actual data point, which would be 69 days, a little bit smaller, the distance from that actual point to the predicted line is smaller, therefore it's better. It's a better model. All right, example 2, a quadratic model. Farmers sometimes use fertilizers to increase crop yield, but often wonder just how much fertilizer they should use. The data shown in the scatter plot below are from a study of the effect of fertilizer on the yield of corn. If you look at number 7, which isn't on the sheet, but you can read it, it's in front of you. The researchers who conducted this study decided to use a quadratic curve to describe the relationship between yield and the amount of fertilizer. Explain why they made this choice. Gosh, if you look at it, in the beginning, the amount of fertilizer, so the amount of fertilizer would increase. So does yield. I before E except after C. So as X increases, which is the amount of fertilizer, so does Y, which is the yield of the crop. But then, I don't know, somewhere around that point, somewhere around 250 kilograms of fertilizer, the yield starts to decrease. There is too much of a good thing. Goodness. Right, the model that the researchers used to describe the relationship was y equals 4.7 plus 0.5x minus 0.001 x squared. X is the amount of fertilizer, kilograms per 10,000 square miles, and Y is the corn yield, and or megagrams per 10,000 square miles. Use this quadratic model to complete the following table, then sketch the graph of this quadratic equation on the scatter plot. All right, so we're going to plug and chug. I've got Y equals 4.7 plus 0.05x minus 3 zeros and a 1 x squared. First I'll plug in x equals 0, which is going to wipe out these two terms and give us y equals 4.7. Next I'm going to plug in x equals 100. 100 squared is 10,000. Oops. My layout here is awful, sorry. So y equals 4.7 plus 0.05 times 100 minus, okay, calculate that. I've got 8.7. Okay, you get what I'm doing? I'm going to push pause and finish this, and you can finish it on your own and fill in your chart. All right, there you go. It's a really basic sketch. You can sketch yours on your scatter plot and just put your curved line fit into all the dots. So number 9, hold on. Number 9, based on this quadratic model, how much fertilizer per 10,000 square meters would you recommend that a farmer use on his cornfields in order to maximize the crop yield? Justify your choice. If you look at your table, for x equals 200, we have 10.7, and for x equals 300, we had 10.7. So somewhere in between there is our max point. You can plug in x equals 225, x equals 250, and I'll get you a value for y, and we'll try to pick a maximum. We're trying to find the maximum y. It looks for x equals 250, my y is 10.95. So I'm going to go with 250. Cool? So that would be about 250 kilograms per 10,000 square miles. Okay, our last example is exponential. How do you tell how old a lobster is? This question is important to biologists and to those who regulate lobster trapping. To answer this question, researchers record data on the shell length of 27 lobsters that were raised in a laboratory and whose ages were known. Okay, if you look, it seems to be exponential. Okay, we had two options for exponential, decreasing and increasing. So for number 10, it says the researchers who conducted this study decided to use an exponential curve to describe the relationship between age and exterior shell length. Explain why they made this choice. If you look, as the length of the exterior increases, the age also increases. If you also look, the change in age is greater as the shell length increases, which just gives us an exponential look. So your age is increasing faster than the shell length is increasing. The model that the researchers used to describe the relationship is given there. See how it's exponential? Y equals 10 raised to a power, where the variable's in the power. So X represents the exterior shell length in millimeters, and Y represents the age of the lobster in years. The exponential curve is shown in the scatter plot below. Does this model provide good description of the relationship between the age and exterior shell length? It looks good to me. That line fits in there very well. That line really fits in there into those dots quite well. So the dots are reasonably close to the line, and the line is always called the model, and actually it's not a line here, it's a curve. It's called a model. If you look at number 12, it says, based on this exponential model, what age is a lobster with an exterior shell length of 100 millimeters? So we're going to look at the model, which is our equation, negative 0.403 plus 0.0063 times 100. The best thing to do is calculate this part first, which I got 0.227, and then in your calculator raise that to the answer, which would be that point, or you can type it in, 0.227, which gives you 1.69 years old. Cool. All right, number 13. Suppose that trapping regulations require that any lobster with an exterior shell length of less than 75 millimeters or more than 150 millimeters must be released. Based on the exponential model, what are the ages of the lobsters with an exterior shell of less than 75 or greater than 150? Explain how you arrived at your answer. I'm going to use our exponential equation. 10 raised to the negative 0.403 plus 0.0063 times 75. 10 raised to the negative 0.403 plus 0.0063. Okay, hold on a second. I'm going to do some calculations. All right, for less than 75 millimeters, I'd say about a year old. So anything less than a year old, they wouldn't be allowed to catch. And then more than 150 millimeters would be about 3.5 years old. So anything 3.5 years and older would not be allowed to catch. Okay, last slide. Your lesson summary. A scatter plot can be used to investigate whether or not there is a relationship between two numerical variables, our x and our y. Linear, quadratic, and exponential functions are common models that can be used to describe the relationship between variables, and then models can be used to answer questions about how two variables are related. That's it. Good job today.